In today's lecture, we are going to discuss about the method of determining the hybridization of a molecule using group theory. There are three major steps involved in determination of hybridization of a molecule using group theory. The first step is writing the reducible representation. The second step is reducing the reducible representation using the reduction formula. The third step is the assigning of hybridization. How the hybridization is assigned. First, we will take up the first step, that is writing the reducible representation. First, we have to write the structure of the molecule. We are going to talk about the molecule boron trichloride. And boron trichloride has trigonal planar shape. All the bonds are in the same plane. Next, we are going to write the point group of the molecule. Since this is a planar triangular molecule, the point group is D3H. And we have to write the symmetry operations present in the D3H, namely E, C3, C2, sigma H, S3 and sigma V. There are 6 types of operations, about which you will see in greater detail later. The next thing is we have to write the basis of the molecule. The basis of the molecule is written by representing each sigma bond by a vector. What do you mean by that? Suppose we have a molecule like this. This is a sigma bond. This is a sigma bond. This is a sigma bond. But this is a pi bond. We have to represent each sigma bond by a vector. That means one vector should be like this. One vector should be like this, representing this sigma bond. Another vector like this. Another vector like this. But you should not write the next vector here for a pi bond. You have to represent only sigma bonds by a vector, not a pi bond. And not just sigma bond, if there is any lone pair, of electrons present, that is, lone pair means non-bonding pair of electrons, they should also be represented by a vector. For example, if you take NH3, the nitrogen will carry a lone pair. So when you write the basis, you have to write like this, like this, like this for the 3 NS sigma bonds, and there should be a fourth vector for the lone pair. So you have to assign a vector for a sigma bond as well as lone pair, but you should not assign a vector for a pi bond. You should not assign a vector for a pi bond. Now, if you look at the structure of BCl3, you will find 3 boron chlorine bonds, all single bonds, so all sigma bonds, and so there should be 3 vectors to represent that, like this. This is the basis. After writing the basis for the molecule by representing each sigma bond by a vector, you have to perform each symmetry operation on this basis. What are the symmetry operations? You find the symmetry operations written down here: E, C3, C2, sigma H, S3, sigma V. All these should be carried out where? On this basis. And what has to be found out? The number of vectors remaining unshifted during operation. You have to find out the number of vectors remaining unshifted during an operation. There is a general thing which you should remember for any element of symmetry, be it axis or plane. During the corresponding symmetry operation, rotation or reflection, whatever atoms or bonds which are whatever vectors that are present on the axis or plane, they will not get shifted. All the vectors remaining directly in the axis or plane will not get shifted. First, we will take up the symmetry operation E. Symmetry operation E is the operation of doing nothing, but that means all the three vectors remain in the same position, nothing is done. So all the three vectors remain in the same position means they are not shifted, and so the number of unshifted vectors is 3. Next we come to the symmetry operation C3. C3 is the axis passing through the boron atom, that is the center of the molecule, perpendicular to the molecular plane. You will find like this. This is the trigonal planar arrangement for the basis. You will find a C3 axis like this, passing through the boron atom, perpendicular to the molecular plane, and when you rotate the molecule through 120 degrees, the vector here will be shifted to this position, the vector here will be shifted to this position, the vector here will be shifted to this position. That means all the vectors are shifted, and so the number of vectors remaining unshifted will be 0. So 0 vector remains unshifted. Next we come to the symmetry operation C2. You must know where is the C2 axis in BCl3 exists. The C2 axis in BCl3 exists along the boron chlorine bond, and it is present in the molecular plane. So when you rotate the molecule, since it is C2, rotate the molecule through 180 degrees. Any vector present in the axis itself, it will not be shifted. There is one vector that is present in the axis, that will not be shifted. This will come to this place and this will come to this place. So two vectors are getting shifted. One vector that is remaining on the axis is unshifted. So the number of unshifted vectors is 1. The next operation is sigma h, the horizontal plane of symmetry. The horizontal plane of symmetry is the molecular plane which is perpendicular to the principal axis C3. Any plane that is perpendicular to the principal axis C3, principal axis, is known as horizontal plane of symmetry. So the molecular plane is horizontal plane of symmetry, like this. All the three vectors lie in this plane. During reflection, any vector lying in this plane will be unshifted, but all the three vectors remain in this plane, and so the number of unshifted vectors will be 3. Next we have the symmetry operation S3. Symmetry operation S3 is made up of a combination of two operations. One is C3 and the other is sigma h. Operations done in this order. Or you can write alternatively like this. This is better. C3 followed by sigma h. Now when you perform C3 operation, what will happen is this will be shifted here, this will be shifted here, this will be shifted here, and all the atoms are getting shifted during C3 operation itself. And now when you reflect it along the perpendicular plane, since already all the atoms are shifted, all the vectors are shifted, since already all the vectors are shifted, there is no unshifted vector, and so 0 vectors remain unshifted. The next operation is sigma v, the vertical plane of symmetry. In the case of BCl3, the vertical plane of symmetry contains a boron chlorine bond, contains a boron chlorine bond. For example, if you assume boron to be present here and chlorine to be present here, the boron chlorine bond will be present in the plane and will bifurcate two other boron chlorine bonds, two other vectors. So there is one vector that is present in the plane itself, and it is perpendicular to the molecular plane. It is perpendicular to the molecular plane. And this is a vertical plane of symmetry since it contains the C3 axis, the principal axis. Since it contains the principal axis, is a vertical plane of symmetry. During reflection about sigma v, the vector that is present in the plane, it will not get shifted. So how many vectors are present in the plane? There is one vector remaining in the plane. So this will shift here, this will shift here, but this will not get shifted, and so the number of unshifted vectors is 1. Now we have completed the 6 operations, and let us summarize. On identity operation, how many vectors remaining unshifted? 3 vectors remaining unshifted. 3 vectors remaining unshifted, and that is why you write the character of reducible representation as 3. So what is the character of reducible representation in this case? The number of unshifted vectors during an operation. Next, during C3, 0 vector remains unshifted, so write 0 here. During C2 operation, 1 vector remains unshifted, write 1. During sigma h operation, 3 vectors remain unshifted, so write 3. During S3 operation, 0 vector remain unshifted, write 0. On reflection about sigma v, 1 vector remains unshifted, write 1. And so what you have now is what is known as reducible representation for determining the hybridization. And these numbers 301, 301 are the characters of irreducible representation. Next, we are going to do the reduction of this reducible representation. This reducing representation has to be reduced. For that, we need the reducible representation, which is described just now and which is written here. And we need the character table for D3H. In the character table, each line A1 dash, A2 dash, E dash, A2 double dash, A1 double dash, A2 double dash, E double dash, etc. These 6 lines are known as irreducible representations. They are known as irreducible representations. The numbers inside 1, minus 1, 0, minus 2, minus 1, etc. are known as characters of irreducible representation. And when you say characters of irreducible representation, chi is written in a slightly different manner. I have not written it exactly. It is somewhat similar to x. Chi I, because character of irreducible representation. These are the numbers which are chi I. These are the numbers in the reducible representation which are chi R. This is chi R. This is chi I. Now here you find 6 columns. 2, 2 plus 2, 6. Leave this. This is the point group. This is the point group. These 6 columns are known as classes of irreducible representation. So there are 6 classes, and inside this class there is only one operation. In this class there are two operations. In this class there are three operations. In sigma h class there is only one operation. In S3 class there are two operations. In sigma v class there are three operations. The number of operations in a class we call it as GP. So GP for C3 is 2, GP for 3 sigma v is 3, number of operations in a class. If you add all the number of all the operations given here, you find 1 plus 2c3, so 2, 3c2 plus 3, sigma h, 1 sigma h plus 1, 2s3 plus 2, 3 sigma v plus 3, you get a number of 12, and that is the total number of operations which is given by the symbol h. So I have introduced you what is a reducible representation, what is an irreducible representation, what is the character of reducible representation, what is the character of irreducible representation, what is meant by GP, the number of operations in a class, what is meant by h, h is the sum of the total number of operations. Now we will go to the reduction formula. So here I have written the number of operations as 12. After that I have written the reduction formula. Number of times, reduction formula is the number of times an irreducible representation is repeated. 1 by h, h is the total number of operations. GP is the number of operations in a class. Chi a is the character of reducible representation. GP is the number of operations in a class. What is it? For the 2c3 class, GP is 2. For 3c2 class, GP is 3. For 2s3 class, GP is 2. What is chi I? Chi I are the numbers present in this character table. What is chi R? Chi R is the character of reducible representation, the numbers present in the reducible representation. What is h? H is the total number of operations. Now let us get on to the aspect of reduction. First we will go for the first irreducible representation. That is, when you say first irreducible representation, what I mean is A1 dash is an irreducible representation. What are you going to find out? Number of times an irreducible representation is repeated. So if I get using this formula the number as 1, that means A1 dash is repeated 1 time. If I get the number as 2, that means it is 2 times repeated. A1 dash is repeated 2 times. If I get the number as 3, A1 dash is getting repeated as 3 times. 1 by h. What is the value of h? H is 12. So 1 by 12. Then summation GP chi A chi R. Let us find out how we find out this summation. For this operation A1 dash, going to the first operation, what is the GP here? 1. And what is the chi I against A1 dash? This number 1. What is the chi R against A1 dash? Again, in the chi A against E in the reducible representation 3. Next go to the, for the same irreducible representation A1 dash, go to the next operation 2c3. Since it is 2c3, GP is 2 and the number in the reducible representation against A1 dash is 1, number in the reducible representation is 0. Next go to the next operation 3c2, next class 3. Since it is 3c2, GP is 3, chi I is 1, chi R is a number in the reducible representation against 3c2, 1. Next is 1 sigma h, GP is 1, chi I is 1 and chi R is 3. Next is 2s3. So GP is true, chi I is 1, the character in front of A1 dash against 2s3, chi R is 0. Then 3 sigma v, GP is 3, number of operations in a class, chi I 1, character of reducible representation, character of reducible representation chi R 1. And if you calculate this, you will get the number as 1. That means A1 dash is repeated only one time. A1 dash is repeated only one time. Likewise, we have to go to the remaining irreducible representation, A2 dash, E dash, A1 double dash, A2 dash, E double dash, A2 double dash, E double dash, everything one by one using the same formula like this. And find out the number of times A2 dash is repeated, number of times E dash is repeated, number of times A1 double dash is repeated, and so on. If you find that, next we come to A2 dash. So you can forget all the other numbers. Now you have to focus only on A2 dash. These are the chi I values. Whatever values that are against A2 dash. These are the GP values. And these are the reducible representation chi R values. And using the formula H is 12. Using this formula you get 0. That means A2 dash is repeated 0 times. A2 dash repeats 0 times. It's not present at all. Next is E dash. Now you have to look at the characters against E dash alone. That is these characters. Forget all the other characters and find out the number of times E dash is repeated. This 1. E dash is repeated one time. Next is A1 double dash. Now you look at the A1 double dash characters alone. Leave the other characters. GP will remain same, 1 2 3 1 2 3. Chi R will remain same, 301 301. Only the chi I will change. H will remain same. And if you calculate the number of times A1 double dash is repeated, it comes out to be 0. That means it is not repeated at all. Next we come to A2 double dash. Consider and similarly do the reduction. We will get the value as 0. A2 double dash is repeated 0 times. Next is E double dash. You consider the characters of opposite E double dash alone, not the remaining characters. GP is same, chi R is same, only the chi I is different. And using the formula calculate the number of times E double dash is repeated, 0. E double dash repeats 0 time. Having completed all the 6 irreducible representations, summarize them. That will be the reducible representation. A1 repeats 1 time, so write A1 dash once. A2 dash repeats 0 times, so you need not write A2 dash. E dash repeats 1 time, write E dash. A1 double dash repeats 0 times, there is no need to write because 0 times A1 double dash is 0. A2 double dash repeats 0 times, E double dash repeats 0 times, so you have only 2 terms, A1 dash and E dash. Using this reducible representation, now you have to assign the hybridization to BCl3. Assigning the hybridization, we need the character table, and in the character table we also need whatever letters that are written on the side of the character table. They are letters like square plus y square z square s square y square x y x z y z. These are known as quadratic coefficients. And you have x, y and z, which are known as Cartesian coordinates. We have rx and ry and rz representing rotation about x axis, y axis and z axis. Now you need the reducible representation. If you find the s square plus y square and z square against the term in the reducible representation, then it represents the totally symmetric combination of s orbitals. If you look at the character table itself, what you will find is against s square plus y square z square you find all ones. That is why you say that it is completely symmetric. If it is negative, it is antisymmetric. Next is s, y, z. They are known as Cartesian coordinates. If you find the Cartesian coordinates against the terms in the reducible representation, it indicates the p orbitals. If you find the quadratic terms given, like s square minus y square, s y, x z, y z, etc., against the term in the reducible representation in the character table, they represent d orbitals. Using this, let us find out from the reducible representation a1 dash plus e dash, which we got early. Let us go back and show you. This is the reducible representation we have got, a1 dash plus e dash. Using this reducible representation, what you have to do is look at the row corresponding to a1 dash first. Again, this, what is the letter which you find here? S square plus y square z square. It indicates what? S square plus y square plus z square indicates s orbital. So this indicates s orbital. Next is e dash, the reducible. Against e dash, look at the character table. You find sy as well as s square minus y square, xy. So you have two options, either xy or s square minus y square sy. If you have xy, it is 2p orbitals, x and y, 2p orbitals, represent 2p orbitals. If you have s square minus y square xy, you have 2d orbitals. So you have two combinations possible. One is s and 2p, sp2, or s and 2d, sd2. But the second one is energetically unfavorable. That means the energy of s and d orbitals are very different. There is a large energy difference between s and d orbitals. That means hybridization of s and d orbitals cannot be carried out. So the hybridization is sp2, and so the hybridization of BCl3 is sp2. Thank you.